Hi, this is Dane Quinn from the University of Akron, and today I will do an example dealing with particle dynamics. Here we have a block of mass m that slides on a smooth surface that is inclined at an angle phi with respect to the horizontal, and the block is pulled by a force of magnitude F up the plane. So here up the plane is defined in the E1 direction. I'd like to find the acceleration of the block. So here we begin by identifying forces that act on the system. So certainly we have the applied load, and that is here, F in the E1 direction. That acts on the system. Then we have the weight, or the force due to gravity, and that I will represent by W. And finally, we have the normal load between the surface and the block. So that I will represent as N. And then the motion here is only in the E1 direction. So notice that as part of the problem statement, we have defined I and J as horizontal and vertical. Then E1 is along the plane, and E2 is perpendicular to the plane. So our next step is to identify coordinates and directions. Well, again, the directions we were given as part of the problem statement. Right, so I'll write those again. I and J, and then E1 is directed along the plane, and E2 is perpendicular to the plane. Then I need to identify a coordinate that will measure the configuration of this system. So remember what coordinates are. They're measurable quantities that specify the configuration, or in this case, where the block is at. There's certainly lots of coordinates that I could define that would tell me and measure the position of the block. But the one that's going to be most natural is a coordinate that measures the displacement in the direction of the motion. So here, let's identify x as the displacement of the block up the plane. So now we can write the coordinates in terms of one another. So here E1 is cosine of phi in the I direction plus sine of phi in the J direction, and E2 is minus sine of phi in the I direction plus cosine of phi in the J direction, while we can also write J and I in terms of E1 and E2. So here I is cosine of phi in the E1 direction minus sine of phi in the E2 direction, while J is equal to sine of phi in the E1 direction plus cosine of phi in the E2 direction. So with these coordinates and directions defined, we can now look at the kinematics, which entails writing the acceleration in terms of the measured coordinates and directions. So again, given x along the plane, the acceleration of the block is simply x double dot in the E1 direction. Now I do want to point out that the acceleration is distinct from this measurement. X double dot is the second derivative of this coordinate, but the acceleration is x double dot in the E1 direction. So they're really different things. Although it's easy to confuse x double dot and the acceleration of the block, let's try to keep the distinction between the scalar and the vector separate. So with that, we'll now turn to the forces. And we had three forces, right? There was this force, that force and this force. And we had defined this as F in the E1 direction. That was actually given in the problem statement. Then we had the weight and the normal force. So now, in terms of the directions and coordinates as necessary, the weight is minus mg in the j direction, while the normal force is in the E2 direction, but we do not know the magnitude. So we'll leave that as an unknown, but we'll specify the direction as E2. So this normal load is N in the E2 direction. And at this point, we are ready to apply the equations of motion. We have all the forces properly described. We have described the acceleration in terms of the coordinates. So now, let's look at the equations of motion. And of course, we'll use linear momentum balance, which is sum of the forces equals mass times acceleration. In particular, the acceleration of the block. But the left-hand side we have from the free body diagram. Let's go back and look at that. So we'll just take these three forces and sum them together. So that gives us minus mg in the j direction. That was the weight. There's the applied load, F, in the E1 direction. And there's the normal load, N, in the E2 direction. On the right-hand side, we identified the acceleration as x double dot in the E1 direction. So now, the left and the right-hand side represents linear momentum balance applied to the block. And notice that this is a vector equation. Right? Each of these terms is a vector. The acceleration is a vector. So vector equations have two components. We can take components in the I and j direction to find two scalar equations, or we can take components in the E1 and E2 directions to find our two scalar equations. Either way, we will find the same answer. These two approaches are exactly the same. They're equivalent. But one oftentimes is better than the other in terms of the algebra that we ultimately have to do. So now let's look at this equation. Our unknowns are N and x double dot. M was given as part of the problem statement. G is known. And the applied load was also given as part of the problem statement. And it's assumed to be a known quantity. So now if I look at these two unknowns, x double dot and N, they are nicely split in the E1 and E2 directions. So in particular, N will have no contribution to the E1 component, while x double dot will have no contribution to the E2 component. And that will lead to algebraic equations that are relatively straightforward, right? In fact, they're decoupled. However, if I were to take components in the I and j direction, then N would contribute to the I and the j direction because E2 has a component in the I and j, as would x double dot. So now these two unknowns would be mixed in the two directions. So let's go ahead and write j in terms of E1 and E2, and then take components in those directions. So looking back at our previous work, j was sine phi in the E1 direction plus cosine of phi in the E2 direction. So I will remind you of that. And then we'll take components in the E1 and E2 direction. So in particular, in the E1 direction, we find minus mg sine, right, that's this piece, plus f from here equals mx double dot. While in the E2 direction, this reduces to minus mg cosine, and then plus n equals 0. Notice there's no component in the E2 direction. So finally, we can solve these for our unknowns, x double dot and n. And because we've chosen carefully, this becomes fairly easy. X double dot is equal to f over m minus g sine of phi, while n is equal to mg cosine. So finally, the acceleration of the block is x double dot in the E1 direction, or f over m minus g sine in the E1 direction. Now, just to give you a little more information and insight about this problem, I can plot the acceleration as a function of the applied load, F. F was assumed to be constant, right? But if I let this be a variable in the system, then again we can find the acceleration as a function of F. And it ends up just being a straight line. So here we might have something that looks like this. Notice that if F is 0, the acceleration is negative, minus g sine of phi. And as F increases, the acceleration just increases linearly. So this value is minus g sine of phi, right, when F is equal to 0. Solving for the force at which the acceleration vanishes gives me F EQ, and EQ here is for equilibrium, because when there's no acceleration, the system is in static equilibrium. So really, we have just solved for the static problem as a special case of our dynamic equations, because static equilibrium implies that x double dot is equal to 0. So at this value, F is equal to mg sine of phi. So again, we're able to look at statics as a special case of dynamics. So in this problem, we have taken the block subject to a force applied externally and gravity, and ultimately gone through our application of linear momentum balance to find the acceleration. And then we've seen that the acceleration depends linearly on the applied load, and kind of as a special case, we've identified the value of the force needed for static equilibrium. If F is anything other than this force, then the block will either move up the plane if F is large enough, or it will slide down the plane for small enough values of F. So that's it for this problem. It's fairly simple, but it's a nice introduction to applying linear momentum balance for these sort of problems with sliding blocks and things. Thank you very much, and I will talk to you again.